What if everything you thought you knew about the universe was mostly invisible? Imagine floating adrift in the inky blackness between star systems, surrounded by, well, by nothing you can actually see. It's a bit like trying to find your phone in a dark room after a power outage, except the room is the entire universe, and your phone is, well, most of the universe. You're adrift in the silent, vast expanse where light simply refuses to go, where the very fabric of reality is woven from something profoundly mysterious. You feel the slight, almost imperceptible tug of something unseen, a gentle whisper of gravity that doesn't quite add up. It's like standing on a dock, watching the water ripple, but there's no boat, no breeze, just ripples. This is your first encounter with the invisible universe beckoning, an invitation to ponder what lies beyond the reach of our most powerful telescopes, what fundamentally shapes the cosmos without ever directly revealing itself. For centuries, we've charted the stars, mapped the galaxies, and felt pretty smug about our understanding of the universe. We've discovered black holes that devour light, nebula that paint the night sky with vibrant colors, and galaxies spiraling majestically through space. But beneath all that dazzling, visible spectacle, there's an undercurrent, a silent, powerful force that makes up the vast majority of everything. It's the universe's biggest secret, and we're only just beginning to get some clues. Think of it like this. You're at a party, and everyone's dancing, laughing, and generally making a visible ruckus. That's the visible matter, the stars, planets, gas, and dust that emit light or reflect it. But then you notice that the entire dance floor seems to be subtly tilting, even though there's no one visibly pushing it, no giant invisible hand at work. That tilting, that inexplicable gravitational influence, is our first hint of dark matter. It's the ultimate wallflower, the shyest kid at the cosmic party. Yet it's the one holding the entire event together. And for the longest time, its existence was purely theoretical, a mathematical placeholder in our cosmic equations, a bit like needing an x in algebra to make the whole thing balance. Historically, our understanding of gravity, largely thanks to Isaac Newton, allowed us to predict the orbits of planets with incredible precision. But when astronomers started looking at objects far beyond our solar system, things got weird. The early cosmic clues started trickling in over a century ago, almost like faint radio signals from a distant galaxy. Picture yourself in the early 20th century, a pioneering astronomer squinting through a telescope at distant nebula, what we now know as galaxies. You're measuring their speeds, their movements, trying to understand the grand celestial ballet. And what you find is perplexing. You expect the outer edges of a swirling galaxy to slow down, much like the outer parts of a spinning merry-go-round. Common sense, right? If you're holding on to the edge, you're moving faster than someone near the center, but the gravitational pull from the center should lessen with distance, causing things farther out to orbit more slowly. But that's not what was observed. The outer stars and gas clouds were moving way too fast, as if they were being held onto by something far more massive than what was visible. It was like watching a figure skater spinning, and her arms, representing the outer parts of a galaxy, were moving just as fast as her core, defying the physics you thought you knew. Historians still argue whether these initial subtle discrepancies were truly recognized as a puzzle piece for dark matter, or merely dismissed as observational errors or some minor cosmic anomaly of the time. But the seeds of doubt were sown. It was almost like discovering that your morning coffee cup weighs 10 times what it should, even though it looks perfectly normal, right? Well, astronomers didn't have the luxury of blaming a faulty scale when it came to the universe. They had the laws of physics, which seemed to be telling them that something was fundamentally missing from their picture of the cosmos. This wasn't just a minor statistical blip. It was a consistent, widespread phenomenon. Imagine the frustration, the delightful scientific irritation of seeing the universe refuse to conform to your beautiful, elegant equations. It's like trying to bake a cake, following the recipe exactly, but when you pull it out of the oven, it's twice as big as it should be and tastes faintly of, well, something you can't quite identify. And you know, for a field that prides itself on precision and predictability, this was quite the cosmic curveball. The universe, in its infinite wisdom, was playing a prank. You continue to observe, the initial confusion slowly giving way to a nascent understanding that something profound is at play. This wasn't just a glitch in the cosmic matrix, it was a fundamental imbalance. The stars in the outer reaches of galaxies, like our own Milky Way, were simply spinning too fast to stay gravitationally bound by the visible matter alone. Imagine a celestial figure skater, arms outstretched, spinning at an impossibly high speed, yet never flying apart. That's the galactic rotation enigma you're witnessing, a puzzle that begged for an invisible solution. According to the laws of gravity as we understood them, the rotational speed of stars and gas clouds in a galaxy should decrease as their distance from the galactic center increases. It's similar to how planets in our solar system orbit the Sun. Mercury, being closest, zips around quickly, while distant Neptune plods along at a much slower pace. The Sun's gravitational pull weakens with distance, and so should the orbital speeds of objects around it. But when astronomers meticulously measured the rotation curves of spiral galaxies, they found something entirely different. They discovered that stars and gas clouds far from the galactic center were orbiting at roughly the same speed as those closer in. It was as if a massive, invisible halo of something was extending far beyond the visible disk of the galaxy, providing extra gravitational glue. If this unseen mass wasn't there, these rapidly moving outer stars should have simply flown off into intergalactic space, like water spinning off a bicycle wheel. Yet they remained gravitationally bound. This was a consistent, undeniable observational fact, not just for one galaxy, but for many. It suggested that a significant portion of a galaxy's mass wasn't emitting light, wasn't reflecting light, wasn't interacting with light in any way that we could detect. It was truly dark, and it was plentiful. This revolutionary idea, however, didn't just pop out of nowhere. Back in the 1930s, a notoriously eccentric but brilliant Swiss astrophysicist named Fritz Zwicky's insight provided some of the earliest, albeit largely overlooked, evidence for this unseen component. Zwicky was observing the Coma cluster of galaxies, a massive collection of thousands of galaxies bound together by gravity. He meticulously measured the velocities of individual galaxies within the cluster and applied what was then cutting-edge physics to calculate the cluster's total mass based on their movements. What he found was staggering. The cluster appeared to be moving far too quickly to be held together by only the visible galaxies within it. He estimated that the visible matter accounted for less than 10% of the mass needed to keep the cluster from flying apart. Zwicky, with his characteristic bluntness, famously coined the term dunkle Materie, German for dark matter, to describe this missing mass. His contemporaries, however, largely dismissed his findings. Perhaps it was his abrasive personality, or perhaps the idea was simply too radical for the time. After all, the universe was supposed to be made of stars and gas, things we could see and measure. The notion of an invisible, pervasive substance seemed outlandish, almost like something out of a science fiction novel. Historians still argue whether Zwicky's genius was truly ahead of its time, or if his pugnacious manner simply alienated the scientific community, preventing his ideas from gaining immediate traction. It's a bit like showing up to a fancy dinner party in a tuxedo and flip-flops. No matter how brilliant your conversation, some people just can't get past the footwear. Fast forward to the 1970s, and a quiet, persistent astronomer named Vera Rubin's revolution truly brought the concept of dark matter into the mainstream. Rubin, along with her colleague Kent Ford, embarked on a systematic study of the rotation curves of spiral galaxies, armed with more precise instruments and a deeper understanding of galactic dynamics. You can imagine her, late at night, hunched over data sheets, meticulously plotting the rotational speeds of stars at varying distances from the centers of dozens of galaxies. And with each new galaxy, the same perplexing pattern emerged. The stars in the outer regions were always moving too fast. Rubin's work was meticulous and undeniable. She repeatedly found that the visible mass of a galaxy simply wasn't enough to explain the observed rotation. Her findings corroborated Zwicky's earlier, more speculative claims, but provided far more robust and widespread evidence. It was no longer an isolated anomaly in one distant cluster. It was a universal phenomenon across galaxies. Her elegant, persistent observations forced the scientific community to confront the uncomfortable truth. The universe, as we saw it, was not all there was. It was like realizing your entire social circle is made up of elaborate cardboard cutouts, and the real people are lurking just out of sight, pulling all the strings. The visible universe, it turned out, was just the tip of a much larger, darker iceberg. Her work ignited a full-fledged scientific quest to understand this elusive substance, transforming it from a fringe idea to one of the most pressing mysteries in modern cosmology. And, bless her heart, she did it with a calm determination that truly exemplified the scientific spirit, proving that sometimes quiet perseverance speaks louder than any bombastic pronouncements. With Vera Rubin's undeniable evidence, the scientific community could no longer ignore the elephant in the cosmic living room. The concept of dark matter shifted from a peculiar anomaly to a fundamental component of the universe. Now, the hunt was on to figure out what this mysterious substance actually was. This led to an exciting and frankly rather speculative period of theoretical physics, as scientists tried to imagine what kind of particles or objects could possess such profound gravitational influence without interacting with light. This is where we get into the realm of WIMPs and machos, the leading theoretical candidates for what dark matter might be made of. Imagine, if you will, the universe running a cosmic most wanted list, and at the top are these elusive suspects. First up, the weakly interacting massive particles, or WIMPs. These are hypothetical particles that are thought to be massive, perhaps many times heavier than a proton, but they interact with normal matter only through gravity and the weak nuclear force. The weak force is responsible for radioactive decay, but it's incredibly short-ranged and, well, weak. This means WIMPs wouldn't absorb or emit light, wouldn't collide with ordinary atoms in a way that generates heat or light, and would essentially pass right through us, the Earth, and even the Sun without a whisper. Think of them as cosmic ninjas, silent, invisible, and incredibly hard to detect, but definitely there, exerting their influence. It's a bit like trying to catch a ghost with a butterfly net. Good luck with that. The appeal of WIMPs is that they fit rather neatly into extensions of the standard model of particle physics, the framework that describes all the known fundamental particles and forces. Many theories beyond the standard model, such as supersymmetry, naturally predict the existence of particles with WIMP-like properties. On the other side of the theoretical coin, we have massive compact halo objects, or machos. Unlike WIMPs, machos aren't exotic, undiscovered particles. Instead, they represent a class of astronomical bodies made of ordinary baryonic matter, the stuff stars, planets, and you and I are made of, but that are simply very, very dim or dark. This could include things like black holes, neutron stars, brown dwarfs, failed stars that aren't massive enough to ignite nuclear fusion, or even rogue planets floating through interstellar space. The idea is that there could be vast numbers of these objects lurking in the galactic halos, providing the missing gravitational pull. For a while, this was a very popular idea. After all, it's easier to imagine lots of dim objects than a whole new type of particle, right? It's like trying to find where all the socks go in the laundry. Sometimes it's just the dryer eating them, not a portal to another dimension. However, observations and experiments over the past few decades have largely ruled out machos as the primary component of dark matter. If there were enough machos to account for all the dark matter, astronomers should have detected more instances of them gravitationally lensing background stars. Essentially, their gravity bending the light from distant stars in a measurable way. While some lensing events attributed to machos have been observed, they are far too few to explain the vast amount of dark matter needed. Plus, cosmological data from the early universe, particularly observations of the cosmic microwave background, which we'll get to later, promise, strongly suggest that dark matter cannot be made primarily of baryonic matter. So, while machos might contribute a tiny fraction, they're definitely not the main event. Historians still argue whether the initial enthusiasm for machos was a reflection of scientific conservatism, a reluctance to embrace truly exotic solutions when more mundane ones seemed plausible. This brings us back to the WIMPs, which remain the leading candidate. The challenge, of course, is detecting something that barely interacts with anything. It's like trying to listen to a whisper in a hurricane. But that hasn't stopped scientists from trying. This quest has led to some of the most extraordinary and sensitive experiments ever conceived, pushing the boundaries of engineering and physics. The underlying principle for direct detection attempts is deceptively simple. If WIMPs exist and are constantly streaming through the Earth, which they would be by the billions every second, then every now and then, just occasionally, one of them might actually bump into an atomic nucleus in a highly sensitive detector. Imagine you're trying to catch a single incredibly tiny frictionless ball in a room full of air. Most of the time, it'll just zip past everything. But maybe, just maybe, it'll graze an air molecule, imparting a tiny bit of energy. That tiny bit of energy, if we can detect it, is our golden ticket. These collisions would be incredibly rare and incredibly faint, producing only a minuscule amount of heat, light, or ionization. To make matters even more challenging, the Earth is constantly bombarded by other particles, cosmic rays from space, neutrinos from the Sun, and natural radioactivity from the Earth itself. These background noise particles would completely swamp the tiny signal from a potential WIMP interaction. So the first order of business for these experiments is to get rid of all that noise. And that, my friend, is where things get seriously creative, and often seriously deep underground. To shield their ultra-sensitive detectors from the incessant cosmic barrage and the constant hum of terrestrial radioactivity, scientists have literally gone to ground, burrowing deep beneath mountains and into disused mine shafts. This is the realm of underground labs, a silent, cold, and surprisingly high-tech world dedicated to catching the faintest whisper of dark matter. You're descending now, deep into the Earth's crust, miles of rock above you acting as a natural shield, absorbing most of the cosmic rays that would otherwise drown out any subtle dark matter signal. It feels a bit like entering a secret lair from a spy movie, except instead of villains, you're battling invisible particles. Imagine walking through long, dimly lit tunnels, the air cool and still. The walls are often rough-hewn rock, but then you turn a corner and suddenly you're in a gleaming, sterile cavern, spotless and meticulously organized. Here, massive tanks filled with incredibly pure liquids or cryostats housing supercooled crystals sit silently. These aren't just any tanks, they are the most sensitive scientific instruments ever built, designed to register an event so rare it might happen only a few times a year, if at all. One such example is the Sudbury Neutrino Observatory, SNOLAB, now SNOLAB, located in an active nickel mine 2 kilometers underground near Sudbury, Ontario, Canada. Yes, right here in Canada, proving that even our rocks are doing vital cosmic work. Historically, these deep underground sites were initially chosen for neutrino experiments, which face similar background challenges, but they proved perfectly suited for the dark matter hunt. The principle behind these detectors is ingenious, if seemingly impossible. Take, for example, experiments that use large vats of liquid xenon or argon. These noble gases are chosen because they can be super purified to remove radioactive contaminants. And when a particle does interact with their atoms, they produce tiny flashes of light or ionization trails. The detector is essentially waiting for a WIMP to collide with a xenon nucleus. When such an interaction occurs, the nucleus recoils, much like a billiard ball being struck by another. This recoil generates a tiny burst of light and free electrons. Sensitive photomultiplier tubes surrounding the liquid detect these flashes of light, and electrodes measure the charge from the electrons. The trick is differentiating this tiny WIMP signal from all the other background noise. It's like trying to hear a pin drop during a rock concert, except you've built a soundproof booth around the pin. Another approach uses ultra-cold crystals, often made of germanium or silicon. These detectors are cooled to temperatures just a tiny fraction of a degree above absolute zero, making them incredibly sensitive to minute changes in temperature. If a WIMP strikes an atom in the crystal lattice, it causes a minuscule vibration which registers as an incredibly tiny rise in temperature. This method is called a cryogenic detector. The precision required is astounding. Scientists are literally measuring temperature changes that are fractions of a millionth of a degree. It's a testament to human ingenuity and our insatiable curiosity about the universe. You might be thinking, this sounds like an expensive way to play cosmic whack-a-mole. And you wouldn't be wrong. These experiments cost hundreds of millions of dollars and involve collaborations of hundreds of scientists worldwide. But the potential payoff, unveiling the dominant component of our universe, is considered worth every penny. Despite decades of effort and increasingly sensitive detectors, a definitive direct detection of a WIMP has yet to be made. This doesn't mean WIMPs don't exist. It simply means they are even more elusive than we initially thought, or that their interactions are even weaker than predicted. It's also possible that the specific types of WIMPs we've been looking for aren't the right ones, or that dark matter isn't a WIMP at all. This lack of direct detection has led some to question the WIMP paradigm, prompting renewed interest in other dark matter candidates, though none have emerged as clear frontrunners. It's a classic scientific dilemma. The absence of evidence is not evidence of absence. Still, the search continues, with new generations of detectors being built, pushing the boundaries of sensitivity even further. Historians still argue whether the prolonged lack of direct detection will eventually lead to a paradigm shift in dark matter research, or if it merely underscores the immense difficulty of the search. While the direct detection experiments are trying to feel dark matter, other researchers are looking for its ghostly fingerprints in the cosmos. This is the realm of indirect detection signals, where scientists search for the byproducts of dark matter particles interacting with themselves. The idea here is that if dark matter particles, particularly WIMPs, are their own antiparticles or can annihilate with their antiparticle partners, they might occasionally collide and annihilate, producing ordinary particles like gamma rays, neutrinos, or antimatter, positrons, and antiprotons. These secondary particles can be detected by telescopes and satellites. It's like looking for the smoke when you can't see the fire. You are now peering through the eyes of orbiting telescopes, searching for telltale gamma-ray glows from dense regions of dark matter, such as the galactic center, or from dwarf galaxies that are thought to be rich in dark matter. These observations involve sifting through vast amounts of cosmic data, looking for subtle excesses of these high-energy particles that can't be explained by conventional astrophysical processes. For instance, some anomalous signals of positrons detected by instruments like the Fermi Gamma Ray Space Telescope have, at times, been tantalizingly interpreted as possible signs of dark matter annihilation. However, these signals are often also explainable by more mundane astrophysical sources, such as pulsars, those rapidly spinning neutron stars that beam radiation like cosmic lighthouses. Distinguishing between a dark matter signal and astrophysical noise is an enormous challenge, requiring exquisite precision and a deep understanding of standard cosmic processes. It's a bit like trying to find a specific grain of sand on a vast beach, armed with only a magnifying glass and a hopeful attitude. But the search continues, fueled by the knowledge that one clear, unambiguous signal could unlock one of the universe's greatest secrets. So, we're building these incredible underground fortresses to catch a WIMP. But what if we could make dark matter ourselves? That brings us to the world's most powerful particle smasher. While underground labs and space telescopes diligently search for faint whispers of dark matter, another powerful tool in the physicist's arsenal is being employed, smashing particles together at incredible speeds. This brings us to the Large Hadron Collider's role, a colossal scientific instrument buried deep beneath the border of France and Switzerland. You imagine yourself standing at the edge of a massive circular tunnel, 27 kilometers, 17 miles in circumference, where protons are accelerated to nearly the speed of light before being made to collide head-on. The LHC isn't designed to directly see dark matter, but rather to create it, or at least to create particles that could be dark matter candidates. Think of it like this. If dark matter particles are incredibly massive and don't interact much, perhaps we can produce them in high-energy collisions, much like how new, unstable particles are routinely created in accelerators. The theory is that if WIMPs or other hypothetical dark matter particles exist, and they are massive, then it takes a lot of energy to create them. The LHC provides exactly that kind of energy. When protons collide, their energy can be converted into mass, potentially forging new exotic particles. If a dark matter particle is produced in these collisions, it wouldn't leave a direct track in the detectors because, by definition, it doesn't interact strongly with matter. It would simply zip away, unseen. However, its presence would be inferred by a missing amount of energy and momentum after the collision. Imagine throwing two billiard balls at each other with immense force, and then, after the collision, you notice that some of the energy and momentum from the initial impact has simply vanished. It's like a magic trick where the magician makes a rabbit disappear, but instead of a rabbit, it's a fundamental property of physics. This missing energy signature is what LHC scientists are looking for. They're meticulously reconstructing billions of collision events, searching for that telltale imbalance. This isn't easy. Countless other known particles can also escape detection, or neutrinos can carry away energy. So the data analysis is incredibly complex, requiring sophisticated algorithms and a deep understanding of particle physics to sift through the noise and identify a potential dark matter signal. Historically, particle accelerators have been instrumental in discovering new fundamental particles, from the W and Z bosons to the Higgs boson, so there's a precedent for this approach to succeed. Despite the LHC's incredible power and ingenuity, it too has yet to definitively produce or detect a dark matter particle. This has led to a lot of head-scratching and a re-evaluation of theoretical models. Does it mean WIMPs are too light to be produced at the LHC, or too heavy? Or does it mean that dark matter is something entirely different, something not predicted by the standard model of particle physics extensions that the LHC is designed to test? Historians still argue whether the initial optimism for LHC dark matter discoveries was overly ambitious, given the sheer difficulty of the problem. It's a bit like building the world's most powerful fishing trawler, casting a net the size of a city, and still coming up empty-handed for that one specific, incredibly rare fish. But the LHC continues to operate, pushing to higher energies and collecting more data, always with the hope that the next collision might reveal the missing piece of the cosmic puzzle. Beyond the cutting edge of particle accelerators and deep underground labs, some of the most compelling evidence for dark matter comes from the faint afterglow of the Big Bang itself. This is where the cosmic microwave background, or CMB, enters the picture, a relic radiation that bathes the entire universe, providing a snapshot of the cosmos when it was only about 380,000 years old. You're looking back in time to a period when the universe was a hot, dense plasma, too opaque for light to travel freely. Then, as the universe expanded and cooled, electrons and protons finally combined to form neutral hydrogen atoms, and suddenly the universe became transparent. The light from that moment, stretched and cooled by billions of years of expansion, is what we observe today as the CMB. Imagine the universe as a giant simmering pot of cosmic soup, and the CMB is the steam rising off it, carrying information about the ingredients and how they were mixed. The CMB isn't perfectly uniform. It has tiny temperature fluctuations, subtle hot and cold spots. These ripples in temperature are incredibly important because they represent the seeds from which all the large-scale structures in the universe, galaxies, galaxy clusters, and the vast cosmic web eventually grew. It's like looking at a topographical map of a perfectly smooth, featureless plain and suddenly noticing tiny, almost invisible bumps and valleys. Those are the primordial seeds. And here's where dark matter comes in. The observed pattern of these temperature fluctuations in the CMB is exquisitely sensitive to the amount of different components in the universe. Our best cosmological models, which describe the evolution of the universe from the Big Bang to today, simply cannot reproduce the observed pattern of the CMB without including a significant amount of dark matter. Baryonic matter, the ordinary stuff, would have been too strongly coupled to radiation in the early universe, meaning its gravitational pull would have been smoothed out by the pressure of light. Dark matter, however, doesn't interact with light, so its gravitational clumps could have started forming much earlier, providing the scaffolding for ordinary matter to eventually fall into and form structures. It's like building a sandcastle. You need a strong, invisible bucket to give the sand its shape before you can decorate it. The CMB data points to a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, which is a whole other cosmic mystery for another sleepy night. This precise ratio is derived from the peaks and troughs in the CMB's fluctuation spectrum. Without dark matter, the peaks would be in the wrong place, and the universe would look fundamentally different from what Planck and WMA satellites have so precisely measured. This evidence is so compelling, so precisely matched by theoretical predictions, that for many cosmologists, the CMB provides the strongest evidence for dark matter's existence, even if we still don't know exactly what it is. It's a cosmic fingerprint that dark matter simply can't hide from.
Beyond the faint whispers of the cosmic microwave background and the elusive hunt in particle accelerators, dark matter reveals its presence through one of the most fundamental forces in the universe, gravity. And gravity, as Einstein taught us, isn't just a force, it's a warping of space-time itself. This leads us to the awe-inspiring phenomenon of gravitational lensing power, a cosmic magnifying glass that allows us to see the invisible. You're now floating in the vastness of intergalactic space, observing light from incredibly distant galaxies. Normally, this light would travel in a straight line, directly to your cosmic eyeball, but not when dark matter is around. Imagine placing a massive, invisible bowling ball on a stretched rubber sheet. The sheet sags, creating a dip. Now roll a marble across the sheet. Instead of going straight, the marble will curve as it passes near the bowling ball, following the contours of the dip. In this analogy, the rubber sheet is space-time. The bowling ball is a massive object, like a galaxy or a cluster of galaxies, and the marble is a beam of light. Gravitational lensing occurs when light from a distant source passes near a massive foreground object, and the gravity of that foreground object bends the light, much like a conventional lens. This bending can distort, magnify, or even create multiple images of the background source. It's a bit like looking through the bottom of a thick, wavy glass bottle. Things on the other side look stretched and blurry, or sometimes you see several distorted versions of the same thing. Dark matter, being the dominant mass component in galaxy clusters, is particularly adept at this cosmic magic trick. When astronomers observe distant galaxies behind massive galaxy clusters, they often see highly distorted, stretched, and often multiple arcs and rings of light. These are the gravitationally lensed images of those background galaxies. If you were to calculate the amount of visible matter in the foreground cluster, the stars, gas, and dust that you can see, it simply isn't enough to cause the degree of lensing observed. The amount of bending implies far, far more mass than is visible. This missing mass, responsible for the extra bending, is attributed to dark matter. One of the most striking examples of this is the bullet cluster, a pair of galaxy clusters that have passed through each other. When these two clusters collided, the ordinary, visible gas, which interacts electromagnetically, was slowed down and heated, forming a distinct cloud in the center. However, the dark matter, which by definition barely interacts, passed right through each other without slowing down. By mapping the gravitational lensing in the bullet cluster, astronomers were able to show that the vast majority of the mass in the cluster, and thus the source of the gravitational lensing, was located separately from the visible gas, exactly where the dark matter was predicted to be. It was like seeing the ghost of the mass, independent of the visible unravel stuff. This observation provided incredibly direct and compelling evidence for dark matter, as it showed that the dominant source of gravity was indeed something invisible and non-baryonic. Historians still argue whether the bullet cluster observation truly settled the debate for good, or if it merely intensified the hunt for the nature of dark matter rather than its existence. The beauty of gravitational lensing is that it's a direct probe of mass, regardless of whether that mass emits light. It's a purely gravitational phenomenon governed by Einstein's theory of general relativity, and it doesn't care if the mass is a shining star or an invisible cloud of dark matter particles. This makes it an incredibly powerful tool for mapping the distribution of dark matter in the universe, even on the largest scales. You can literally create dark matter maps of galaxy clusters and filaments of the cosmic web by analyzing how light from distant objects is distorted. It's like having X-ray vision, but for gravity. And speaking of the cosmic web, dark matter isn't just passively sitting there bending light, it's actively sculpting the very large-scale structure of the cosmos. This brings us to dark matter's structure, its crucial role in forming the intricate filamentary network that spans the universe. You are now seeing the universe not as isolated galaxies, but as a vast, interconnected tapestry, a cosmic web of matter, with enormous voids separating the dense filaments.
In the early universe, after the Big Bang, matter was distributed relatively smoothly. But there were tiny, primordial density fluctuations, like subtle wrinkles in the fabric of space-time, as we saw with the CMB. Due to its inability to interact with light and its weak interactions with itself, dark matter was able to start clumping together much earlier than ordinary baryonic matter. Without the pressure from photons pushing it around, dark matter's gravity could get to work, pulling more dark matter towards these slightly denser regions, forming gravitational potential wells. Think of these wells as invisible gravitational anchors, forming before the ordinary matter could even get its act together. Ordinary matter, which was still coupled to radiation, would then fall into these pre-existing dark matter halos as the universe expanded and cooled. It's like having a pre-built invisible scaffolding upon which all the visible structures are assembled. Without dark matter, these initial density fluctuations in ordinary matter would have been too small, and the universe would have been too smooth for galaxies and galaxy clusters to form within the age of the universe. Gravity on its own, with only ordinary matter, simply isn't strong enough or fast enough to build the cosmic structures we see today in the allotted time. So, if you look out at the night sky and marvel at the billions of galaxies arranged in vast superclusters and filaments, you're essentially looking at the gravitational legacy of dark matter. It's the architect of the cosmic web, the invisible hand that pulls everything together, literally. And while we joke about the universe's peculiarities, the fact that its very framework is built upon something we can't see is perhaps its greatest and most humbling jest. As you contemplate the vast, invisible scaffolding of the cosmic web, held together by dark matter, it becomes abundantly clear that our current understanding of the universe, specifically the standard model of particle physics, is incomplete. Dark matter pushes the boundaries of this meticulously constructed framework, which has successfully described all known fundamental particles and forces, excluding gravity, for decades. You're now at the frontier of physics, where the known gives way to the profoundly unknown, a bit like realizing your beautifully organized bookshelf is missing an entire genre of books you didn't even know existed. The standard model, for all its triumphs, predicting the existence of particles like the Higgs boson and explaining the intricate dance of quarks and leptons, has no place for dark matter. Every particle described by the standard model interacts with light in some way.
way, either by emitting it, absorbing it, reflecting it, or being affected by it electromagnetically. But dark matter, by its very definition, does none of these things. It's an outsider, a rogue element that doesn't fit into the meticulously arranged periodic table of particles we've built. It's like finding a mysterious, incredibly heavy, perfectly transparent object in your living room that responds to nothing but gravity. What do you even call it? How do you describe its properties within your existing vocabulary? This forces physicists to confront the humbling reality that the Standard Model, while incredibly successful, is not the final word on the nature of reality. It means there's physics beyond the Standard Model, new particles and forces waiting to be discovered. This is both a challenge and an incredible opportunity. The very existence of dark matter is a powerful signal that our current understanding of the fundamental building blocks of the universe is incomplete. It's a bit like discovering a giant uncharted continent on Earth after centuries of believing you'd mapped everything. Exciting, terrifying, and utterly game-changing. Historians still argue whether the perceived crisis in particle physics due to the lack of new discoveries at the LHC beyond the Higgs would have been even more profound if not for the compelling evidence of dark matter pointing to new physics. So, what could this beyond the Standard Model physics entail? Many theoretical frameworks propose extensions to the Standard Model that naturally accommodate dark matter candidates. One of the most popular is supersymmetry, which posits that every known Standard Model particle has a much heavier superpartner. For example, the electron would have a selectron and the photon a photino. In many supersymmetric models, the lightest supersymmetric particle, LSP, is stable and has the properties of a WIMP, making it an ideal dark matter candidate. Another intriguing possibility involves extra dimensions, where particles could propagate into dimensions beyond our three spatial ones, and dark matter might be such a particle. The mind boggles, doesn't it? It's like discovering that your house isn't just a two-story building, but actually has secret rooms extending into other dimensions that you can't even perceive. The lack of direct detection of WIMPs, as we discussed, has also prompted theorists to explore even more exotic possibilities. What if dark matter isn't a single type of particle, but a whole dark sector of particles with their own set of dark forces, interacting with each other, but only very weakly with our visible matter? This concept is gaining traction, suggesting that the universe might be far more complex and populated than we ever imagined, with parallel invisible universes interacting with ours only through the gravitational pull of their dark inhabitants. It's like realizing that your backyard isn't just home to squirrels and birds, but a whole secret society of highly advanced, invisible squirrels with their own intricate social structures and, crucially, their own invisible nuts. You're now moving into the future, a future driven by the tantalizing promise of finally unraveling this profound mystery. This brings us to the future mystery solving in dark matter research, a multi-pronged approach involving new detectors, innovative experimental designs, and even space-based observatories. The journey is far from over. In fact, in many ways, it's just beginning to accelerate. On the ground, the next generation of direct detection experiments are being planned and built, designed to be even more sensitive than their predecessors. These ton-scale detectors, using vast amounts of liquid xenon or argon, aim to increase the chances of a rare WIMP interaction by simply having more target material. Projects like LZ, Lux Zeppelin, and Exxon Xenont are already operational, pushing the limits of sensitivity further than ever before. These detectors are essentially bigger and quieter versions of the ones we discussed earlier, hoping that, if you listen long enough and loud enough, that faint whisper will become an undeniable shout.
It's a continuous arms race against background noise, where every tiny improvement in purity or shielding can make a difference. Imagine trying to hear a mosquito sneeze in a library. You need absolute, total silence. As you consider the ongoing and future efforts to unravel the dark matter enigma, you realize the sheer scale of human ambition involved. It's a quest that spans continents and even extends into the cold vacuum of space, pushing the limits of technology and our understanding of the cosmos. This continuous effort in future mystery solving is a testament to our enduring curiosity, a refusal to accept that something so fundamental can remain hidden forever. The large liquid xenon detectors like LZ and Exxon Xenont, now operational, are meticulously collecting data. Imagine them as colossal, silent sentinels buried deep underground, patiently waiting for that one almost imperceptible ping that signifies a dark matter particle has finally brushed against one of their precious xenon atoms. These experiments are designed to be so sensitive that even tiny vibrations from distant earthquakes or minute radioactive contamination within their own materials could mimic a dark matter signal. So, the engineering prowess required to maintain such pristine conditions, to isolate these detectors from literally everything, is mind-boggling. It's like trying to play a delicate violin solo in the middle of a bustling construction site. You need absolute, total silence. But what if WIMPs, as traditionally conceived, aren't the answer? The scientific community is a vibrant marketplace of ideas, and the lack of a definitive WIMP detection has spurred a diversification of the dark matter search. You're now seeing a proliferation of experiments designed to detect lighter dark matter candidates, such as axions. Axion detection experiments often involve strong magnetic fields, attempting to convert axions into photons, light particles that can then be detected. These are often tabletop experiments, a stark contrast to the massive underground caverns, showing the diversity of approaches in this field. It's a testament to scientific creativity that researchers aren't putting all their dark matter eggs in one WIMP basket. Beyond these direct and indirect detection methods, the universe itself continues to be our largest laboratory. Space-based observatories, free from the distorting effects of Earth's atmosphere, are providing unprecedented views of the large-scale distribution of dark matter. Missions like the European Space Agency's Euclid telescope, launched in 2023, are meticulously mapping billions of galaxies across vast swaths of the sky. By analyzing the subtle distortions in the shapes of these distant galaxies due to gravitational lensing, Euclid is creating an unparalleled 3D map of the dark matter distribution in the universe. This isn't about detecting individual dark matter particles, but about understanding how the invisible scaffolding of dark matter has shaped the cosmic web over billions of years. It's like trying to understand an invisible sculpture by looking at how light bends around its form. Another upcoming mission, the Nancy Grace Roman Space Telescope, formerly WFIRS, from NASA, also set to launch later this decade, will also contribute significantly to dark matter mapping through its powerful gravitational lensing capabilities and its ability to survey vast areas of the sky with incredible resolution. These missions will help us constrain the properties of dark matter, not just its amount, but perhaps hints about its self-interaction or its temperature, whether it's cold or warm dark matter, which impacts how structures form. You're effectively building a comprehensive cosmic resume for dark matter, even if you can't see the candidate directly. But the future of dark matter research isn't just about bigger experiments or fancier telescopes. It's also about theoretical innovation. What if dark matter doesn't fit into any of our current particle physics frameworks? What if it's something entirely new, something so alien to our current understanding that we haven't even conceived of the right way to look for it? This brings us to a wonderfully speculative yet critically important area of research:
research, exploring completely novel dark matter candidates and detection mechanisms. For example, some theories propose dark photons, hypothetical particles that could act as intermediaries between dark matter and ordinary matter, allowing for a very weak, previously undetected interaction. Other ideas involve feebly interacting massive particles, WIMPs, which would have interacted very little with the primordial plasma in the early universe, leaving a different signature than traditional WIMPs. It's like realizing your cosmic detective kit needs a whole new set of tools because the suspect is using a disguise you've never encountered before. The universe is a vast laboratory, and we're just beginning to learn how to properly conduct our experiments within it. The sweet dreams of tonight are built on the exciting realities of future discovery.
You find yourself at the precipice of discovery, recognizing that the long, arduous road of scientific inquiry is often paved with more questions than answers, especially when grappling with something as elusive as dark matter. The ongoing debate and diversification of research approaches highlight a fundamental truth about science. It's a living, breathing process of refinement and re-evaluation. The future mystery-solving continues its relentless march forward, driven by an insatiable curiosity that seems to be hardwired into the human condition. One exciting frontier in this multi-pronged assault on the dark matter mystery involves exploring ultralight dark matter candidates, such as the aforementioned Axions, but also even more exotic possibilities like fuzzy dark matter. Fuzzy dark matter posits that dark matter particles are incredibly light, so light that their quantum wave-like properties become significant on galactic scales. Instead of individual particles, you'd have a vast, coherent wave of dark matter permeating galaxies, impacting their structure in unique ways. It's like imagining a galaxy isn't just sitting in a cloud of invisible particles, but rather submerged in a cosmic fluid that sloshes around, influencing everything through its wave mechanics. This theory offers intriguing explanations for some galactic anomalies the traditional WIMP dark matter struggles with, such as the core cusp problem, where simulations predict a denser dark matter core in galaxies than observations suggest, and the too big to fail problem, where simulations predict more small dark matter halos than observed dwarf galaxies. To detect these ultralight particles, scientists are developing entirely different types of experiments. For Axions, this involves concepts like haloscopes, which use powerful microwave cavities embedded in strong magnetic fields to try and convert axions into detectable photons. Imagine a highly sensitive radio receiver tuned to an incredibly specific faint frequency, hoping to pick up a signal that no one else can hear. These experiments are extremely challenging due to the minuscule expected signal, but the potential payoff, a revolutionary discovery, makes the effort worthwhile. For fuzzy dark matter, the evidence would come more from astrophysical observations, looking for the telltale ripples and patterns it imprints on galactic structures and cosmic distances. It's like being a detective looking for footprints, but the suspect floats just above the ground, leaving only subtle distortions in the air itself. The exploration of dark sectors, where dark matter might be part of an entire hidden universe of particles and forces, is also gaining traction. This idea suggests that dark matter doesn't just interact gravitationally, but might have its own dark forces that govern interactions within the dark sector. Our visible world would be like one island in an archipelago, with other islands existing in a separate dark dimension, rarely interacting with our own except through gravity. This opens up a vast theoretical playground, prompting physicists to imagine new experiments that could potentially detect these subtle dark sector interactions.
For instance, some experiments might look for tiny deviations from known forces, or unexpected decays of ordinary particles into dark sector particles. It's a bit like discovering that your neighbor, whom you thought was a quiet, solitary person, actually hosts elaborate, invisible dance parties every night, and you only notice the subtle vibrations coming through the floor. Historians still argue whether the concept of a dark sector will prove to be a fruitful new paradigm or a testament to the ever-increasing complexity of theoretical physics in the absence of definitive experimental results. Alongside these direct and indirect searches, cosmological simulations continue to be an indispensable tool. Supercomputers are churning through petabytes of data, simulating the evolution of the universe from the Big Bang to the present day, incorporating different dark matter models. By comparing the results of these simulations, the formation of galaxies, clusters, and the cosmic web, with actual astronomical observations, scientists can constrain the properties of dark matter. It's like running a vast, complex experiment in a virtual universe, trying out different recipes for cosmic ingredients until the simulated universe looks just like our own. These simulations help guide experimental efforts, telling physicists what kinds of dark matter might be plausible and where to focus their search. They've been instrumental in solidifying the cold dark matter model, which suggests dark matter particles move slowly, allowing structures to form hierarchically from small clumps to larger ones. The sheer technological ingenuity required for all these endeavors is staggering. From ultra-pure materials and cryogenic cooling systems that approach absolute zero, to advanced photon detectors and algorithms capable of sifting through unimaginable volumes of data, the pursuit of dark matter is pushing the boundaries of what is scientifically and technically possible. It's a truly global effort, with collaborations spanning multiple countries and institutions, demonstrating the collective power of human intellect when faced with a grand unifying mystery. You consider the profound implications of this ongoing search. If dark matter is indeed discovered and its properties fully understood, it would not only revolutionize particle physics, demanding a complete overhaul or significant expansion of the standard model, but also reshape our entire understanding of cosmology. It would tell us about the very early universe, about the fundamental forces at play, and about the ultimate fate of the cosmos. It's a discovery that would resonate through every field of science, touching upon our philosophical understanding of existence itself. And in the quiet hum of your own thoughts, you feel a connection to this vast, silent, and deeply mysterious component of the universe, knowing that the quest for its truth continues unabated.
You're deep in thought, processing the vast implications of dark matter for the very foundations of physics. It's not just a missing puzzle piece, it's a profound challenge to the edifice of our scientific understanding. The Lambda CDM model, our reigning cosmological paradigm, is incredibly successful at explaining the universe on large scales. The expansion, the cosmic microwave background, the distribution of galaxies and galaxy clusters. But its reliance on invisible dark matter and dark energy means there are fundamental components it describes but does not explain. It's a bit like having a perfectly functional car, but two of its most critical components are labeled Mystery A and Mystery B under the hood. The tension in the Hubble constant measurements is a prime example of where the Lambda CDM model faces challenges, and where the nature of dark matter could potentially offer clues. The Hubble constant describes the current expansion rate of the universe. Measurements derived from the early universe, like the CMB, interpreted through Lambda CDM, disagree with measurements from local, more recent observations, like Type A supernova. This discrepancy, known as the Hubble tension, is one of the hottest topics in cosmology right now. Could the properties of dark matter, or perhaps a slight interaction with it, somehow influence the expansion rate in a way that resolves this tension? Perhaps a tiny fraction of dark matter decays over cosmic time, subtly altering the energy density of the universe and thus its expansion. Or maybe it has very weak interactions beyond pure gravity that we haven't accounted for. Historians still argue whether the Hubble tension represents a genuine crack in the lambda CDM model or merely indicates unknown systematic errors in our measurements. It's a high-stakes scientific detective story, with the universe itself as the crime scene. Another area where dark matter's precise properties matter deeply is in galaxy evolution. We've established that dark matter forms the gravitational scaffolding, the initial halos into which ordinary matter falls to form galaxies. But the finer details of galaxy formation, how spiral arms form, how galaxies interact, and even the abundance of small dwarf galaxies are still subjects of intense research, and dark matter plays a critical role in these processes. For instance, observations suggest that some dwarf galaxies, those small faint companions to larger galaxies, appear to have less dark matter than predicted by standard cold dark matter simulations. This is known as the missing satellites problem, or the too big to fail problem. If dark matter particles had some very weak self-interactions, they might occasionally collide and scatter off each other within a halo, smoothing out the dark matter density and potentially resolving some of these small-scale discrepancies. It's like discovering that your Lego structure doesn't quite match the instruction manual for the small intricate bits, and realizing the Legos themselves might be a bit stickier than you thought. Furthermore, the interaction, or lack thereof, between dark matter and ordinary matter is crucial. We assume it only interacts gravitationally, but what if there's a tiny, almost imperceptible interaction through a fifth force? Just recently, researchers have been conducting ultra-precise measurements of atomic energy levels, looking for tiny deviations that could signal the presence of a new, incredibly weak force, mediated by a dark photon or similar particle. These experiments are pushing the boundaries of precision measurements to astonishing levels, akin to trying to weigh an individual atom by noting a fractional change in the Earth's gravitational field. If such a force exists, it could provide a direct portal into the dark sector, offering a new way to interact with and potentially even detect dark matter beyond its gravitational pull. The theoretical landscape for dark matter candidates has expanded far beyond the initial WIMPs and Axions. While these remain leading contenders, the absence of direct detection has spurred incredible creativity. You are now considering a whole menagerie of hypothetical particles. Sterile neutrinos. These are heavier, hypothetical cousins of the known neutrinos, which interact even more weakly than their standard model counterparts. They could be produced in the early universe and survive to form dark matter. SNINOs. In some supersymmetrical theories, the superpartner of the neutrino, the SNINO, could be a dark matter candidate. Dark photons. As mentioned, these would be the force carriers of a hypothetical dark electromagnetism, mediating interactions within a dark sector and perhaps with our matter via kinetic mixing. Hidden sector particles. This is a broad category encompassing various particles that belong to a hidden or dark sector of physics, interacting with our visible universe only through gravity or extremely weak portal-like interactions.
Imagine an entire parallel set of fundamental particles and forces, almost a mirror universe, existing alongside our own. The sheer diversity of these theoretical models underscores the difficulty and the potential reward of this scientific quest. Each new candidate requires new experimental approaches, new technological innovations, and a renewed commitment to the unknown. It's a bit like a cosmic game of Guess Who, except you don't even know what the possible characters look like or what rules they play by. The ultimate breakthrough in dark matter could come from any one of these avenues, or from an entirely unexpected direction. Perhaps a new, incredibly sensitive detector reveals that faint WIMP recoil. Maybe a space telescope picks up a definitive gamma-ray signature from dark matter annihilation in a dwarf galaxy. Or perhaps the Large Hadron Collider, with its next round of upgrades, finally creates a dark matter particle and reveals its missing energy signature. What if, here in Toronto, a new experiment at a university lab, designed for an entirely different purpose, stumbles upon an anomaly that can only be explained by a new form of matter? The beauty of science is that the universe is under no obligation to conform to our expectations, and the most exciting discoveries often emerge from the unexpected. The stage is set for one of the greatest scientific revelations of our time.
As you continue this cosmic contemplation, you're struck by the sheer persistence of the scientific endeavor, the collective human drive to pierce through the veil of the unknown. The pursuit of dark matter is not merely an academic exercise, it's a testament to our boundless curiosity and our capacity for ingenuity. The cosmic microwave background, CMB, that faint afterglow of the Big Bang, remains one of our most powerful tools in understanding dark matter's profound influence on the early universe. We've touched upon it, but let's dive deeper into how this ancient light provides such compelling evidence. Imagine the universe shortly after the Big Bang, a mere 380,000 years old. Before this point, the cosmos was a superheated, opaque soup of fundamental particles, protons, electrons, photons, all tightly coupled together. Light couldn't travel freely. It was constantly scattering off free electrons, making the universe effectively foggy. It was like being inside a thick cloud, unable to see anything beyond a few feet. As the universe expanded, it cooled. Eventually, it cooled enough for electrons and protons to combine and form stable neutral hydrogen atoms. This event, known as recombination, was a game changer. Suddenly, the universe became transparent, and the photons, light particles, that had been trapped were finally free to stream across the cosmos. This first light is what we observe today as the CMB, stretched and cooled by billions of years of cosmic expansion until it now appears as microwave radiation, just a few degrees above absolute zero. The CMB is incredibly uniform across the sky, almost perfectly smooth. But precisely measured by satellites like COBE, WMAP, and most recently Planck, there are tiny temperature fluctuations, variations of only a few parts in 100,000. These aren't random, they're the fossilized imprints of density fluctuations in the early universe, the primordial seeds from which all future cosmic structures would grow. Think of them as the earliest blueprints for galaxies and galaxy clusters. It's a bit like looking at an old, faded photograph of a baby and being able to tell from the subtle contours of its face how it will look as an adult. And here's where dark matter steps onto the early cosmic stage.
In the very early superheated plasma, ordinary baryonic matter, the stuff stars and us are made of, was strongly coupled to radiation. The pressure from photons would have smoothed out any gravitational clumps of ordinary matter, preventing them from growing significantly. It's like trying to build a sandcastle on a vibrating table. Any structure you try to build just collapses. Dark matter, however, interacts only through gravity and potentially the weak force if it's a WIMP, meaning it wasn't coupled to the radiation. It could start clumping gravitationally much earlier than ordinary matter, forming gravitational potential wells even while the universe was still opaque. So, when recombination happened and the universe became transparent, the ordinary matter fell into these pre-existing dark matter wells. The pattern of peaks and troughs in the CMB's power spectrum, a mathematical representation of these temperature fluctuations, is incredibly sensitive to the precise amounts of ordinary matter, and dark energy in the universe. If there were no dark matter, the peaks in the CMB spectrum would be in the wrong places, and the relative heights of those peaks would be different. Our current lambda CDM model, with its specific proportions of cosmic ingredients, provides an astonishingly good fit to the observed CMB data. This is why cosmologists consider the CMB one of the strongest pillars supporting the existence of dark matter. It's not just a theoretical convenience, it's an observational necessity for the universe to look the way it does. This cosmic fingerprint of dark matter is so clear that it suggests that dark matter existed and played a crucial role even before the first stars had formed. It determined the large-scale distribution of matter in the cosmos, setting the stage for the formation of everything we see today. Historians still argue whether the elegance of the CMB's fit with the lambda CDM model might lead researchers to prematurely dismiss alternative theories of gravity. But for now, the CMB speaks loudly and clearly for dark matter. It's like having the detailed blueprints of a magnificent building, and those blueprints clearly show an invisible, load-bearing framework that holds everything together. You can't see the framework directly, but you know it must be there because the building stands. The journey continues with another powerful gravitational phenomenon, one that offers a more direct visual confirmation of dark matter's presence: gravitational lensing. We touched on this earlier, but let's delve into its nuances, particularly how it allows us to literally map the invisible. You're observing a distant galaxy cluster, a colossal collection of thousands of galaxies bound by gravity. Beyond this cluster, much further away, lies a background galaxy. As light from this background galaxy travels towards you, it passes through the enormous gravitational field of the foreground cluster.
According to Einstein's theory of general relativity, massive objects warp the space-time around them. This warping then bends the path of light, much like a conventional glass lens bends light to focus or magnify an image. In strong gravitational lensing, where the foreground object is very massive and aligned just right, you can see dramatic effects. Multiple images of the same background galaxy, stretched into luminous arcs, or even forming perfect Einstein rings. It's a breathtaking cosmic mirage, a stunning visual confirmation of space-time distortion. Imagine looking at a distant street lamp through the bottom of a wine glass and seeing multiple distorted versions of the light. That's essentially what strong lensing is, but on a cosmic scale. The key insight for dark matter is this: when astronomers calculate the total mass required to produce the observed gravitational lensing effects in a galaxy cluster, they invariably find that it's far greater than the mass of the visible stars, gas, and dust. The discrepancy is often by a factor of 5 or 6. This missing mass must be invisible, non-luminous, and it must be exerting a powerful gravitational pull.
That, my friend, is dark matter at work, directly revealing its presence through the distortion of light. The bullet cluster, which we've mentioned, remains the poster child for gravitational lensing evidence of dark matter. This remarkable system consists of two galaxy clusters that have passed through each other. Observations show that the hot, X-ray emitting gas, which is ordinary baryonic matter, was slowed down by drag forces during the collision and now lags behind the main clumps of mass. However, gravitational lensing maps clearly show that the bulk of the mass, and thus the dark matter, passed straight through, relatively unaffected, just as expected for a non-interacting substance. It's like watching two trains collide. The baggage, visible matter, scatters everywhere, but the train cars themselves, dark matter, just pass through each other. This visual separation of ordinary matter and the gravitational mass is incredibly compelling. It really is hard to argue with a picture, especially one painted by gravity itself. And for astronomers, these gravitational lens systems are not just curiosities. They are powerful cosmic scales, weighing the invisible components of the universe with exquisite precision. The universe, as we're discovering, is far more intricate and dynamically shaped by the invisible than previously imagined. The gravitational lensing phenomenon and the precise maps of the cosmic microwave background provide irrefutable evidence of dark matter's pervasive influence. But it's not just about its existence. It's about how this mysterious substance orchestrates the grand cosmic ballet, leading us into the fascinating realm of dark matter's structure. You're now visualizing the universe on its grandest scales, where galaxies aren't isolated islands, but rather bright jewels strung along an invisible, intricate web. This cosmic web is the largest known structure in the universe, a vast foam-like network of filaments and sheets of matter interspersed with enormous, relatively empty voids. And the primary architect of this web is dark matter. Imagine a giant spider web spun across the entire cosmos. But the silk strands are invisible. The luminous galaxies we see are like tiny dewdrops clinging to these invisible threads, congregating at the intersections and along the denser parts of the filaments. This structure is a direct consequence of the gravitational instability that arose from tiny density fluctuations in the early universe, amplified over billions of years. In the very early universe, as we've discussed, matter was nearly uniformly distributed. But slight overdensities, like barely noticeable bumps on a perfectly smooth surface, existed. Dark matter, being immune to the radiation pressure that smoothed out baryonic matter, could begin to gravitationally collapse into these overdense regions much earlier. These regions became the seeds for what would eventually grow into dark matter halos, invisible clumps of dark matter. As the universe expanded, these small dark matter halos continued to grow, attracting more dark matter and eventually ordinary matter into their gravitational embrace. This growth wasn't perfectly spherical. Due to slight anisotropies, these clumps preferentially grew into elongated filaments and flattened sheets, leaving vast empty regions or voids in between. It's like watching dough rise, where some parts expand faster and pull the rest into stringy networks. Computer simulations, often called n-body simulations, have been absolutely crucial in understanding this process. These simulations literally model the gravitational interactions of billions of dark matter particles over cosmic timescales, starting from the conditions observed in the CMB. And what emerges from these simulations time and time again is this unmistakable cosmic web structure. The simulated universe looks remarkably like the observed universe, with its galaxies clustered along filaments and in superclusters. If you run these simulations without dark matter, the universe ends up looking far too smooth, without enough time for the large-scale structures we see today to have formed. It would be like trying to build a skyscraper without a steel frame. It just wouldn't stand. The success of these simulations, particularly those using cold dark matter, CDM, has cemented the CDM model as the prevailing paradigm. Cold refers to the velocity of the dark matter particles. They move relatively slowly, not at relativistic speeds, allowing them to clump efficiently on small scales. If dark matter were hot, like neutrinos, which move very fast, its high velocity would smooth out small density fluctuations, preventing the formation of small dark matter halos, and thus small galaxies. This is why standard neutrinos cannot be the dominant form of dark matter. If all dark matter were hot, the universe would have a much more diffuse, less structured appearance on small scales. So, the clumpy, hierarchical structure of galaxies, from dwarfs to giant clusters, is a direct consequence of dark matter being cold, or at least warm enough to clump. This is a subtle yet profound point. The very texture of the universe, the granularity of its structure, tells us something about the nature of dark matter, not just its quantity. Recent observations are even beginning to directly confirm the existence of these elusive cosmic filaments. Using advanced telescopes like the Very Large Telescope, VLT in Chile, and even the James Webb Space Telescope, astronomers are now detecting faint glows from hydrogen gas concentrated in these filamentary structures, often illuminated by distant quasars acting like cosmic flashlights. These direct observations of gas flowing along the dark matter highways further validate the cosmic web model. It's like finally seeing the faint shimmer of those invisible spider silk in the right light. Astronomers in Toronto, for instance, are leveraging Canadian-built instruments to study these very structures, contributing to this global effort. Historians still argue whether the initial theoretical predictions of the cosmic web were considered a speculative leap of faith or an inevitable outcome of the prevailing cosmological models. The ongoing mapping of dark matter distribution through gravitational lensing surveys like those from the Euclid and Rubin space telescopes will continue to refine our understanding of this invisible architecture. These maps are not just pretty pictures. They are crucial data sets that allow cosmologists to test different dark matter models, putting constraints on its self-interaction, its velocity, and ultimately its particle nature. Every subtle distortion of light from a distant galaxy, every clump and void in the cosmic web, whispers clues about the universe's primary gravitational constituent. It's a grand cosmic archaeological dig, where the relics are patterns in the sky, and the tools are telescopes and supercomputers. And as you drift deeper into this understanding, you realize that the most beautiful structures in the universe are built on foundations we cannot see, by an architect we have yet to fully comprehend.
You're beginning to grasp the profound implications of dark matter, not just as a cosmic mystery, but as a driving force behind the universe's evolution. It's the silent majority, dictating the dance of galaxies and shaping the very scaffolding of the cosmos. Now, let's widen our gaze even further and understand how the existence of dark matter inherently challenges and propels us beyond the standard model of particle physics. It's like discovering that the meticulously crafted blueprint for your house, which you thought was complete, somehow omitted the entire foundation and load-bearing walls. The standard model, as we know it, is a monumental achievement of human intellect. It elegantly describes all the known fundamental particles, quarks, leptons like electrons and neutrinos, and force-carrying bosons like photons, and 3 of the 4 fundamental forces, electromagnetic, strong nuclear, and weak nuclear forces. It's been tested to incredible precision in particle accelerators worldwide, from CERN to Fermilab, and has consistently delivered accurate predictions. For example, the discovery of the Higgs boson in 2012 at the Large Hadron Collider completed the Standard Model, explaining how particles acquire mass. It's a truly beautiful and robust theory, the bedrock of modern particle physics. However, the Standard Model in its current form simply has no place for dark matter. Every particle it describes interacts with light or other Standard Model particles in some way that we can detect. Dark matter, by its very definition, does not. It doesn't emit light, absorb light, or reflect light. It doesn't seem to interact via the strong nuclear force, otherwise it would clump differently, or the electromagnetic force, otherwise it would emit or absorb photons. While it theoretically interacts via the weak nuclear force, if it's a WIMP, and, crucially, gravity, these interactions are so incredibly feeble that it makes detection immensely challenging. This is the crux of the problem. Dark matter is a massive, ubiquitous component of the universe that our most successful theory of matter and forces cannot explain. It's the ultimate party crasher that no one invited and no one can see, but who clearly ate all the snacks. This glaring omission means that the Standard Model is incomplete. Its success in explaining visible matter and forces is undeniable, but it's a success only for a tiny fraction, about 5%, of the universe's total mass energy content. The vast majority, approximately 27% dark matter and 68% dark energy, lies firmly outside its purview. This isn't a minor tweak, it's a fundamental challenge that demands new physics. It means there are particles and possibly forces out there that are utterly unknown to us, inhabiting a dark sector that interacts with our visible sector primarily through gravity. The theoretical response to this challenge has been vibrant and diverse. Physicists are actively developing and exploring various extensions to the Standard Model, each proposing different dark matter candidates and interaction mechanisms. This includes supersymmetry, SUSY. As discussed, SUSY is a theoretical framework that posits a superpartner for every known Standard Model particle. The lightest supersymmetrical particle, LSP, is often stable, massive, and weakly interacting, making it an ideal WIMP candidate. If SUSY is correct, the LHC might yet discover these superpartners, providing indirect evidence for the existence of WIMPs. It's like finding a matching sock to a mysterious fancy sock you've had for years, finally confirming it wasn't just a random lonely sock. Extra dimensions. Some theories propose the existence of additional spatial dimensions beyond the familiar three. Dark matter particles could be Standard Model particles that are excitations in these extra dimensions, or entirely new particles confined to these hidden dimensions. Their weak interaction with our visible matter might be explained by their existence in these unseen realms. This idea often features in science fiction, but it's a serious concept in theoretical physics. New force carriers, dark photons, etc. The concept of a dark sector implies that dark matter particles might interact with each other via their own set of forces, mediated by dark force carriers, analogous to our photons. A dark photon, for instance, might feebly interact with our ordinary photons, providing a tiny portal through which dark matter could be detected. This is a bit like finding a secret faint radio frequency that only a few specific weird devices can tune into. The beauty of this pursuit is that it's forcing physicists to think outside the box, to confront the limitations of their most cherished theories, and to imagine entirely new frameworks for understanding reality. The absence of direct detection, far from being a failure, is simply guiding the search, pointing towards candidates that are even more elusive or fundamentally different than initially conceived. It's like having a treasure map, arriving at the X, digging, and finding nothing, which then forces you to reconsider the map's interpretation or the very nature of the treasure. This journey into the unknown pushes the limits of scientific inquiry. The sheer intellectual courage to propose and then meticulously test these highly speculative theories without immediate experimental confirmation is a hallmark of cutting-edge physics. And it underscores a mainstream historical fact in science. Paradigm shifts often occur when existing theories fail to explain persistent observational anomalies. Dark matter is perhaps the biggest, most persistent anomaly in modern physics and cosmology. Historians still argue whether the slow pace of discoveries beyond the Standard Model will eventually lead to a truly revolutionary theoretical breakthrough, or if we are simply in a prolonged period of incremental refinement. You reflect on the vastness of the universe and the equally vast landscape of theoretical possibilities that dark matter has unveiled. It's a compelling reminder that our knowledge is always provisional, always subject to refinement and sometimes complete upheaval in the face of new evidence. The universe is under no obligation to be simple or to conform to our current understanding. And the fact that such a large portion of it remains shrouded in mystery means the most exciting discoveries likely lie ahead, waiting for the right theory, the right experiment, or perhaps the right moment of cosmic inspiration. And as you close your eyes, you realize that the answers to these profound questions might be just around the cosmic corner.
The precise measurements of the universe's composition, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, are derived from a confluence of observational evidence, including the cosmic microwave background, Type A supernova, which reveal the universe's expansion history, and galaxy clustering. This lambda CDM model is currently our best cosmological model, and it relies fundamentally on the existence of dark matter. If dark matter were somehow proven not to exist, or its properties were drastically different, this entire successful model would collapse, requiring a complete rewrite of our cosmological narrative. It would be akin to discovering that the Earth is in fact flat, and all those satellite images and round-the-world flights were just an elaborate optical illusion. Finally, the nature of dark matter has profound implications for the ultimate fate of the universe. If dark matter particles are indeed stable and long-lived, they will continue to exert their gravitational influence indefinitely. If the universe were dominated solely by matter, both ordinary and dark, its fate would depend on the total density of that matter. Either it would eventually collapse in a big crunch if density is high enough, or expand forever but at a decelerating rate if density is too low. However, with the accelerating expansion driven by dark energy, the picture changes. Dark matter will continue to cluster, forming ever larger structures in the cosmic web. But these structures themselves will be increasingly isolated from each other as the intervening space expands faster and faster. Galaxies and galaxy clusters will remain gravitationally bound, but they will eventually lose sight of each other as the light from distant objects gets stretched beyond detectability.
So, while dark matter helped build the cosmic cities, dark energy is ensuring they become increasingly lonely outposts in an ever-expanding void. It's a wonderfully bittersweet cosmic irony, isn't it? The very stuff that brought structure to the universe will ultimately be part of its isolation. You're deep in thought, processing the vast implications of dark matter for the very foundations of physics. It's not just a missing puzzle piece, it's a profound challenge to the edifice of our scientific understanding. The lambda CDM model, our reigning cosmological paradigm, is incredibly successful at explaining the universe on large scales, the expansion, the cosmic microwave background, the distribution of galaxies and galaxy clusters, but its reliance on invisible dark matter and dark energy means there are fundamental components it describes but does not explain. It's a bit like having a perfectly functional car, but two of its most critical components are labeled Mystery A and Mystery B under the hood. The tension in the Hubble constant measurements is a prime example of where the lambda CDM model faces challenges, and where the nature of dark matter could potentially offer clues. The Hubble constant describes the current expansion rate of the universe. Measurements derived from the early universe, like the CMB, interpreted through lambda CDM, disagree with measurements from local, more recent observations, like Type A supernova. This discrepancy, known as the Hubble tension, is one of the hottest topics in cosmology right now. Could the properties of dark matter, or perhaps a slight interaction with it, somehow influence the expansion rate in a way that resolves this tension? Perhaps a tiny fraction of dark matter decays over cosmic time, subtly altering the energy density of the universe and thus its expansion. Or maybe it has very weak interactions beyond pure gravity that we haven't accounted for. Historians still argue whether the Hubble tension represents a genuine crack in the lambda CDM model or merely indicates unknown systematic errors in our measurements. It's a high-stakes scientific detective story, with the universe itself as the crime scene. Another area where dark matter's precise properties matter deeply is in galaxy evolution. We've established that dark matter forms the gravitational scaffolding, the initial halos into which ordinary matter falls to form galaxies. But the finer details of galaxy formation, how spiral arms form, how galaxies interact, and even the abundance of small dwarf galaxies are still subjects of intense research, and dark matter plays a critical role in these processes. For instance, observations suggest that some dwarf galaxies, those small faint companions to larger galaxies, appear to have less dark matter than predicted by standard cold dark matter simulations. This is known as the missing satellites problem, or the too big to fail problem. If dark matter particles had some very weak self-interactions, they might occasionally collide and scatter off each other within a halo, smoothing out the dark matter density and potentially resolving some of these small-scale discrepancies. It's like discovering that your Lego structure doesn't quite match the instruction manual for the small intricate bits and realizing the Legos themselves might be a bit stickier than you thought. Furthermore, the interaction, or lack thereof, between dark matter and ordinary matter is crucial. We assume it only interacts gravitationally. But what if there's a tiny, almost imperceptible interaction through a fifth force? Just recently, researchers have been conducting ultra-precise measurements of atomic energy levels, looking for tiny deviations that could signal the presence of a new, incredibly weak force, mediated by a dark photon or similar particle. These experiments are pushing the boundaries of precision measurement to astonishing levels, akin to trying to weigh an individual atom by noting a fractional change in the Earth's gravitational field. If such a force exists, it It could provide a direct portal into the dark sector, offering a new way to interact with and potentially even detect dark matter beyond its gravitational pull. The theoretical landscape for dark matter candidates has expanded far beyond the initial WIMPs and Axions. While these remain leading contenders, the absence of direct detection has spurred incredible creativity. You are now considering a whole menagerie of hypothetical particles. Sterile neutrinos. These are heavier, hypothetical cousins of the known neutrinos, which interact even more weakly than their standard model counterparts. They could be produced in the early universe and survive to form dark matter. Sneutrinos. In some supersymmetric theories, the superpartner of the neutrino, the sneutrino, could be a dark matter candidate. Dark photons. As mentioned, these would be the force carriers of a hypothetical dark electromagnetism, mediating interactions within a dark sector and perhaps with our matter through kinetic mixing. Hidden sector particles. This is a broad category encompassing various particles that belong to a hidden or dark sector of physics, interacting with our visible universe only through gravity or extremely weak portal-like interactions. Imagine an entire parallel set of fundamental particles and forces, almost a mirror universe, existing alongside our own. The sheer diversity of these theoretical models underscores the difficulty and the potential reward of this scientific quest. Each new candidate requires new experimental approaches, new technological innovations, and a renewed commitment to the unknown. It's a bit like a cosmic game of Guess Who, except you don't even know what the possible characters look like or what rules they play by. The ultimate breakthrough in dark matter could come from any one of these avenues, or from an entirely unexpected direction. Maybe a new, incredibly sensitive detector reveals that faint WIMP recoil. Maybe a space telescope picks up a definitive gamma-ray signature from dark matter annihilation in a dwarf galaxy. Or perhaps the Large Hadron Collider, with its next round of upgrades, finally creates a dark matter particle and reveals its missing energy signature. What if, here in Toronto, a new experiment at a university lab designed for an entirely different purpose stumbles upon an anomaly that can only be explained by a new form of matter? The beauty of science is that the universe is under no obligation to conform to our expectations, and the most exciting discoveries often emerge from the unexpected. The stage is set for one of the greatest scientific revelations of our time.
The dark matter mystery is arguably one of the greatest scientific challenges of our era. It forces us to confront the fact that our understanding of the universe, for all its sophistication, is still profoundly incomplete. It inspires a global, collaborative effort that transcends borders and disciplines, pushing the boundaries of technology and human ingenuity. The answers, when they come, will not only reveal the nature of the universe's invisible scaffolding, but also fundamentally reshape our matter, forces, and the very fabric of reality itself. The cosmic dance continues, and with each passing year, the veil over its silent orchestrator grows thinner. The future of dark matter research is not just about finding a particle, it's about unveiling an entirely new chapter in the story of the cosmos. WIMP hunt continues, but parameter space narrows. Experiments like LZ, Lux Zeppelin, and XNNT, the leading direct detection WIMP experiments, continue to report world-leading exclusion limits. They've pushed the boundaries of sensitivity to unprecedented levels, effectively shrinking the possible interaction strength and mass range for WIMPs. While no direct detection has occurred, these results are invaluable, ruling out many theoretical WIMP models and guiding the next steps. The strategy now involves even larger detectors and more advanced background suppression techniques, some of which are already operational.
axion and light dark matter searches gaining traction. With WIMP searches coming up empty, there's a growing focus on lighter, more elusive dark matter candidates like axions and dark photons. Experiments like ADMX and newer broadband approaches such as BRED, Broadband Reflector Experiment for Axion Detection, which recently released its first results, are pioneering new techniques to detect these particles. These often involve highly sensitive magnetic fields and novel quantum technologies, including those utilizing sapphire crystals as quantum bits, qubits, to sense tiny vibrations from dark matter interactions. The cosmic dance continues, and with each passing year, the veil over its silent orchestrator grows thinner. Cosmological observatories deliver powerful indirect evidence. Space telescopes and ground-based surveys continue to provide compelling indirect evidence for dark matter. The Hubble Space Telescope, with new observing techniques, is revealing that dark matter forms even smaller clumps than previously thought, aligning with cold dark matter predictions. The Dark Energy Spectroscopic Instrument, DESI, is creating the largest 3D map of the universe. And while primarily focused on dark energy, its data on galaxy clustering directly informs dark matter models. The upcoming Vera Rubin Observatory, launching in late 2025, will conduct a decade-long survey of the southern sky, providing an unprecedented movie of the cosmos. Its immense data volume will allow for detailed studies of gravitational lensing and stellar streams, revealing the distribution of dark matter and potentially even the properties of small dark matter clumps in our own galaxy, down to masses lower than ever before. This is particularly exciting for understanding the small-scale crisis in dark matter simulations.
LHC continues to probe for missing energy. The Large Hadron Collider at CERN continues to smash protons together with ever-increasing energy. While a direct dark matter signal, missing energy, hasn't been confirmed, the LHC remains a crucial tool for probing physics beyond the Standard Model. Any new particles or interactions discovered could have direct implications for dark matter. Recent collisions of oxygen at the LHC demonstrate the diversity of its research program. Theoretical models diversifying. The absence of a clear direct detection has invigorated theoretical physics. Beyond standard WIMPs and axions, new concepts like dark sectors, entire hidden universes of particles and forces, fuzzy dark matter, where particles behave more like waves, and even extremely massive Planckian interacting dark matter, PIDM, are being explored. Experiments searching for tiny deviations from known forces, like those using ultra-precise measurements of calcium atoms to look for a fifth force, are exploring subtle portals to these dark sectors. The future of the hunt. Looking ahead, the next decade promises an explosion of data and potentially groundbreaking discoveries. Next-generation direct detection. Generation 3, G3, direct detection experiments, even larger and more sensitive than LZ and Xenon-T, are in the planning stages. These will push the limits of WIMP detection even further, potentially reaching the neutrino floor, where cosmic neutrinos themselves become a significant background. Diverse light dark matter experiments. The landscape of axion and dark photon searches will continue to expand with new technologies. From larger haloscopes to novel quantum-enhanced detectors using superconductors and levitating magnets, the variety of experimental approaches reflects the uncertainty but also the promise of this realm. Advanced cosmological surveys. Beyond Rubin and Euclid, future cosmological surveys will continue to map dark matter with unprecedented precision.
These include missions like SPHEREx, Spectrophotometer for the History of the Universe, Epoch of Reionization, and ISIS Explorer, set for launch in early 2025, which will create detailed maps of the universe in infrared light, providing new insights into galaxy distribution and the cosmic web. Gravitational wave astronomy. The burgeoning field of gravitational wave astronomy, with instruments like LIGO and Virgo, and future space-based detectors like LISA, could also contribute. While primarily searching for black hole mergers, they might one day detect signatures of primordial black holes, a niche dark matter candidate, or even the subtle gravitational waves from the very early universe that could hint at dark matter's origins. Novel theoretical frameworks. The interplay between experimental results and theoretical models will be critical. As parameter space shrinks for existing candidates, theorists will be forced to develop even more radical yet testable ideas. This ongoing dialogue between observation and theory is the engine of scientific progress. Sweet dreams.